Many of you already know Go, one of the oldest surviving board games on Earth. It is also very hard. Just think that in 2016, a mathematician named John Trump and his collaborators sat down and computed the exact number of legal 19 by 19 Go positions. The answer? It was roughly 10 to the 170th power. To put that into perspective, here are the number of atoms in the observable universe and the legal positions of chess. This complexity emerges from rather simple rules. Two players take turns placing their stones on the vacant intersections on the board. A single stone, or a connected group of stones, is captured when surrounded by the opponent's stones on all orthogonally adjacent points. The game proceeds until neither player wishes to make another move. A really good analogy is that you can think of it as two neighbors dividing up a garden. Both want to control the most territory, and whoever manages to control the most territory wins. That's generally all you need to know for this video, but I really recommend to go play a game. I promise it's more fun than you might think. Sometime in the 1970s, a mathematician named John Conway was watching people play the game of Go, and he noticed something. Toward the end of the game, the board tends to fall apart. The single-bit fight becomes a handful of small disconnected fights, each one sitting in its own little region. Conway asks a fundamental question. Can we calculate the state of the entire game simply by adding up these independent sub-games? This same question is what led him to build a completely new number system. So let's build it the way he did, starting from Go. But first of all, what is a game? A game, G, is a pair of sets, L and R, each consisting of other games. The elements of L are called the left options, and the elements of R are called the right options. These represent the moves available to the left player and the right player respectively. From now on, we will refer to left as the black player and right as the white player. In case you hadn't noticed, this definition doesn't say whose turn it actually is. It just describes what each side could do if it were their turn. The convention is that left is the positive player and right is the negative player. This means that a game's value tells you how good the position is for left. As I mentioned earlier, we will operate under the assumption that we are in the endgame, and so instead of looking at entire board positions, we shall analyze only portions of the Go ban, and use the convention that the stones framing our diagrams are safe. Now that we've prepared the ground, let's build the simplest possible game. We will start with a position where neither player has any legal move at all, and call this the zero game. And we will write it like this. Nobody can do anything, and the play contributes 0 to the game. A zero game is really not that interesting. So let's take a look at a game that can actually be played. It's clear that black has exactly one move, and white has none, since suicide and passing are forbidden. After black's move, neither player has any moves left. So the final position is just the zero game. This game G also goes by the name 1. It's not a coincidence that this number system lines up with the Go concept of territory, but we still have some work to do. Now that we know 0 and 1, let's look at a slightly more complex example. If black plays, the game goes to the position we have just seen. So we note that with 1. And if white plays, we would move to this other game. Notice that in white's game, we would also go back to situation 1, but in this case, black would be taking a prisoner. We must therefore give black some kind of compensation for capturing a stone, to differentiate the situations. From now on, captured stones of the opponent's color become a player's prisoners, and are worth 1 point. We call this game 2, as by the simplicity theorem, 2 is the simplest integer strictly between 1 and 3. This pattern generalizes completely. Consider any game where the opponent has no chance to leave or start a co-fight, which is a short loop in which a single stone is captured and another single stone immediately taken back. Suppose that the game contains n empty intersections and m white stones. Then the value of the game will be g equals n plus 2m, and that's because captured stones have the double effect of freeing territory and adding captive points. So far, every example we've built has landed on an ordinary integer, but nothing in Conway's definition requires that. For example, 1/2 represents a situation where black is up half a point. Notice that the contents of 1/2 are 0 on the left and 1 on the right, which means that if it's white's turn, white can change the position to a 0, and if it's black's turn, black can change the position to a 1. Thus, the following, in the middle of a Go board, might have value 1/2. Following Conway's intuition, and as we are constructing a number system, we can add numerical games, and that corresponds to evaluating multiple situations in distinct parts of the Go ban. Then you can see what the whole game's worth. Of course, this is only practical in the endgame. To understand this concept, let's look at a fun example. You can see that the upper area is worth minus 1/2 points, as it's good for white, and so it can become game 1 for white, or game 0 for black, depending on who starts first. We denote it as negative, as those are points that favor white. The lower section is worth minus 5/4, as if black played first, the game would be worth 1, and if white started first, the game would be 2. Again, we use the negative notation. We can conclude then that the total worth of these two games is minus 7/4. But there is another interpretation of the values of games. Let's hear it directly from its creator.
And then after a time, I realized something, which is, rather than thinking of these games as representing numbers of moves and so on, you could think of numbers as games.
The name Surreal Numbers was coined by Donald Knuth, and they are defined in the same way as games, but with one restriction. Each element of L must be strictly less than each element of R. So we can safely say that every surreal number is a game, but not all games are surreal numbers. For example, the game 00, which we call star, is not a surreal number. So the class of games is more general than the surreals, and has a simpler definition. Surreal numbers are constructed rather strangely. The recursive method to construct them goes like this. Every day you can use the existing surreal numbers to build new ones. I know this sounds strange, so I'll let an example lead the way. On day 0, the only option is nothing on both sides, and we call that 0. On day 1, now that we have 0, we can use it to create 0 left, which is equal to 1, and 0 right, which is minus 1. So more than 0 and less than 0. On day 2, we already have 0, 1 and minus 1. So what can we build from them? Well, new numbers start appearing everywhere. What happens if we put 1 on the left and nothing on the right? We get 1 left, which is equal to 2. There's nothing above 1 to stop it, so the simplest number bigger than 1 is just 2. So in just one day, we've extended the number line outward and filled in the gaps. Every number on every day is defined as the simplest value strictly between its left options and its right options, thanks to the simplicity theorem. I won't demonstrate it here, but I linked some resources that I consulted and that helped me understand this concept. So check them out in the description. Now let's consider the omega day, which is none other than the first infinite day. We call omega the first infinite number. On that same day, we also get epsilon, which we can also call 1 over omega, which is the first infinitesimal number. Still considering infinity, after an infinite number of stages, infinite subsets become available, so that any real number A can be represented. So we've just built a number system which collects all the real numbers and all the hyperreal numbers. Isn't that great? Now that we've seen the more abstract theory, we can go back to Go to make an interesting observation about games. As we've seen, Go games are not necessarily surreal numbers, so not every Go position settles into a clean number. Some, like a single dame point, which is a place where placing a stone grants 0 points, which is the start game, are not a number. So it naturally follows to divide games into 3 categories. We say that a game is called if it can be represented by a number. In called games, there is no incentive to move at all, as it leads to decreasing the value of the action. We say that a game is tepid if it's not a number, but left is equal to right, for example the start game. To conclude, a game is hot when whoever gets to move gains something substantial, so L is greater than R, for example 5 minus 2. To continue with the analogy of temperature and numbers, we introduce the most important operation in the combinatorial analysis of Go, which is used to impose on unsettled positions a move tax of 1 point. This technique is called chilling, and it is what actually lets professional players evaluate endgame sequences and measure just how urgently a position needs to be played. You can think of it as the hot potato game. If the potato is burning your hands, you will want to throw it away as soon as possible. Whereas if it's cooler, you may prioritize other strategies. Just like that, in Go, some moves require immediate attention, whereas others can wait. Let's see how it works on the actual board. Let's try to chill a dame, which is a completely neutral point. Neither move makes any territory. So the raw game is just star. Chill it by 1 and you get -1, 1, which, by the simplicity rule, collapses to exactly 0. And if anything, that's the most sensible answer for a dame. By taxing the moves, the chill value tells you that the neutral point is worth 0. So as we've seen, this operator cools off games. In this case, it meant transitioning from a tepid game to a cold game. Let's have a look at another example. Check out this little edge position. If black plays first, he locks in 1 point, and if white plays first, it collapses to star. So the whole thing is 1 star. Now chill it by 1. You subtract 1 from black's options, and add 1 to white's, and star just vanishes, leaving you with 0, 1, which is exactly 1/2. And that's the fun part, because that's literally what Go players regard as a half a point move. Our math is confirming the intuition of players. Anyway, that's the video. If you liked it or if this sent you down the same rabbit hole it sent Conway down, let me know in the comments. And subscribing generally helps a lot, so if you're feeling it, hit that button. See ya!